So first of all, thanks so much for joining the Aviation Data Science Seminar Series again this semester. Obviously, we do apologize for the delay with the ongoing circumstances regarding COVID-19. We've needed to move everything remotely, as most things have, but we're happy to announce that we have a slate of speakers for the next 3 weeks to round out the semester. And as you probably just heard, we will be recording these sessions, so for future consumption. So today, I'm happy to introduce Dr. Mark Hansen, who is a professor of civil and environmental engineering here at Berkeley. He received his bachelor's from Yale in physics and his master's in city planning and Ph.D. in engineering science from Berkeley. He previously worked as a physicist at the Environmental Protection Agency, and he joined the Berkeley faculty in 1988. Here at Berkeley, he's led transportation research projects in urban transportation planning, air transport systems modeling, air traffic flow management, aviation systems performance analysis, aviation safety, aviation environmental analysis, and air transport economics. And Dr. Mark Hansen is also the co-director of Berkeley's Next Door program. Today, he will talk about data analytics for flight trajectories and trajectory anomalies. So without further ado, I'll hand over the reins to Professor Hansen. And I believe he'll start showing the video. Perfect. All right, great. I'm gonna mute myself. And sorry, just as a quick note, if everyone can mute their mics and remove their video, we'll probably have the best communication link for everyone. So thank you.
Pavan, I'm told that the host, who I assume is you, has disabled participant screen sharing.
Oh, 1 second. Here we go. Can you try that again now?
Yes, perfect.
Awesome.
All right. Pavan, can you see my screen?
Yes, we can see it.
Yeah.
Yep.
All right. Well, I'd like to thank Pavan for continuing to, for his persistence and enabling the seminar to continue. I know it's taken a lot of effort to set this all up. And so I really appreciate that. I really appreciate, I'm hearing a lot of background noise. Are other people hearing that too?
Yes, we are. If everyone can mute outside of Professor Hansen, that would be great, just so that we can get a clear channel for listening.
Yeah, thank you everyone for taking some time out to listen to my talk. Of course, there are certain disadvantages to operating via Zoom for this purpose, but there are also some real advantages in terms of being able to chat questions and kind of participate in a variety of ways. So I hope you will avail yourself of that. I would be perfectly happy to stop and attempt to address your questions as I proceed. Pavan has agreed to kind of monitor the chats and other channels like hand raising, I guess people may want to use. And so I will be hearing from him if you guys have any questions, and I'll stop and take a look at what you've got. All right, so my talk today, as promised, is called Data Analytics for Flight Trajectories and Trajectory Anomalies. And this is reviewing several different pieces of work that I've done over the past several years with two students in particular, Yilin Liu and Lu Dai. And this is my outline. So a quick background and motivation, and then the meat of the talk. I'll talk first about trajectory clustering methods, then trajectory assignment models, which is a form of trajectory prediction. Another form of trajectory prediction is generative trajectory prediction models, so I'll speak a little bit about that. And one of the use cases for modeling and analyzing trajectories is looking for anomalous trajectories, and there's a particular example of that I'll present at the end. So why do we engage in this kind of work, flight trajectory analysis? There's several different purposes. One is to be able to predict trajectories in real time, both in situations where, for example, we'd like to have the most accurate prediction of where a particular flight will be at a particular time, or when a particular flight will be at a particular place. So that's one example of trajectory prediction. Performance analysis was kind of where we got started in this, looking at trajectory analysis in order to understand the sources of flight inefficiency in the NAS. I won't talk so much about that particular application here, but some of the things I'll talk about were motivated by that question. And then related to this is also looking at safety analysis, again, looking at both factors that contribute to the occurrence of certain safety critical events related to anomalous trajectories. I'll be focusing on go-arounds in this discussion. And also being able to do real-time prediction in that context. So these are some of the reasons to do it, and what are some of the challenges in actually using flight trajectories for these purposes. The data is typically very voluminous. Trajectory information is coming in on the order of every, say, 5 seconds or so. It is unstructured in the sense that although we have, say, many flights going from point A to point B, there's not a clearly organized set of trajectory information that is automatically generated. So we have to kind of organize the data before we can use our typical data science tools. And also the data can be noisy as well. A second kind of challenge is related to feature engineering around these trajectories. And that typically involves matching the trajectories to other data sets that are also large and difficult to work with, such as winds, convective weather, and other such features. We'll talk more about that later. So the first thing I want to talk about in a little more technical detail is clustering methods. So what are we trying to do with trajectory clustering? So here's a case in point. These are the black lines on the left. I guess I'll start using my pointer here. So these are all represent trajectories of flights going from Houston Intercontinental to Boston, or it could be Boston to Houston. I am actually not sure in this particular case. But in any case, over a period of time, say a year or so, there are many such flights, and we see the black lines indicating what those flight routes are. And there's clear evidence that although each trajectory is unique, there are certain common general paths that the trajectories take. And what we're trying to do in trajectory clustering is starting with this relatively unstructured data for the individual trajectories to get to a picture of the trajectories that looks like this. So this has identified the trajectory clusters, and it also has identified certain flights that are not part of any cluster, what we might call as outlier flights, outlier trajectories. It also has, we identify here, kind of nominal, what we call nominal trajectories, which are kind of the best representation of each of these clusters. So this one, for example, is the best representation of the red cluster. So the first part of this is just a quick overview of how we make that transition that you saw on the previous slide. And so there is established kind of ways of doing this. The first is to clean the data, look for trajectories which show discontinuities, for example, and exclude those. Also, for our particular purpose, we don't want to get into the details of the departure and approach phases of the flight. So we'll just look at the trajectories beginning out and ending outside the terminal areas. So we've said one of the challenges of the trajectory data is that it's kind of disorganized in the sense that there's not a clear structure. And step one is the way that we begin to get that structure. And this is called trajectory resampling. So going from the initial trajectory data, we want to get new trajectories that have equal numbers of points. And we use a linear interpolation for this with respect to the distance flown. So while the raw trajectories, some of them contain more points than others, after this step, we've summarized each trajectory with, in our particular example, 100 points. The next step is 100 points is still a lot to work with, and there's a lot of correlation between those points. So we do a dimension reduction step, and we basically perform a principal component analysis on the 100 variables that represent the trajectories after step one. And what we find typically is we can capture about 90% of the variation with about 5 components. So now we have a very low dimensional, nicely organized data set, basically 5 variables representing each of those trajectories. And in our case, we use that to, we use a DB scan as our clustering method. And so that's what results in the actual trajectories that come out. As some of you know, there are many, many ways of clustering, and DB scan is just one such way. One advantage of DB scan that we like is that it doesn't force every flight into a cluster. And it seems from the first plot and our experience in aviation that there will be kind of one-off flights that should not be forced into a particular cluster. So that's DB scan accomplishes that. All right. Pavan, I'm seeing some comments. Is there anything I should know?
So we were thinking about getting to the questions at the end in the event that you don't answer the question during the talk itself. But for the sake of just moving forward, Augustine had asked, is the trajectory analysis 3D or just 2D?
The trajectory analysis that's a very good question. Is Yulin here? maybe not. I believe that it's 3D, but you've exposed the fact that I didn't actually do the work. For most purposes, we focus on the 2D aspect.
And there is a dimension of time additionally, right?
It's the original data is 3D data, yeah.
I can answer this question.
Okay.
The code is designed for 3D, but I think most of the analysis for the prediction part you can use only 2D.
Great. Thank you, Lou.
Welcome.
All right, so in the spirit of Pavan's admonition, I'll press on. So these are just some results that we get from doing this for your viewing pleasure. This is, I think, from Boston to Houston. No, this is from Houston to Boston. So we like to construct these plots and kind of ponder them and admire them. So what you see in this particular case is that there are 5 clusters, and you can see some summary information about the clusters over on the right here. This is the fraction of flights in each cluster, and these violin plots give us a summary of the inefficiency of the different trajectories in each cluster. By inefficiency, we basically mean with respect to a great circle route. So, for example, in this particular case, the red cluster, the median inefficiency is about 4%. We see that in this particular case, there are 3 quite common routes, and then 2 less common ones. And we also see that about 6% of the flights are not clustered at all based on the DB scan. And those tend to be more inefficient with the median about 8%. So there's one example. Here's another example. This is for Boston to Houston, going in the other direction. And you see there are 2 quite common clusters here, and they also tend to be quite efficient in terms of that en route inefficiency metric. There are 3 other clusters, and then, as before, a set of outlier trajectories. Here's another one for JFK Fort Lauderdale. In this particular case, there's really one dominant route, the red one here, with a few other routes that are flown quite much less often, and again, a few outlier routes, although they're less common in this case. And finally, this is San Francisco to Orlando, and this is another case where there's one dominant route and then several routes that are not one-of routes but are less common. So that's the first part of my talk, just talking about this method for clustering trajectories. The second part, I want to talk more about how we model the what I call trajectory assignment. And so here is kind of at the most challenging version of this problem, which we haven't really tackled yet, although I think it would be an interesting thing for someone to take on. So if we go back and look at that, all those trajectories between Houston and Boston, there are a lot of flights, a lot of trajectories, and as we said, each trajectory is unique. So it would be interesting to just try to understand how can we model which flight took which trajectory. So we have n flights, we have n trajectories, and how can we, what patterns can we tease out, what insights can we tease out from trying to predict which of the unique flights chose the unique trajectory that it did. So this is kind of an end-to-end matching problem, and we've haven't quite taken this on yet, but we have taken on a simpler version of this problem, which is one of the motivations for the cluster assignment, cluster analysis we reported on before. So instead of modeling the assignment of flights to itineraries, we can model the assignment of flights to clusters. And that's what we'll be talking about in these next few slides. So we can go back and look at each flight and see which cluster it belongs to in terms of its itinerary. And then we can try to understand that assignment process. Why did this particular flight end up being assigned to this particular cluster? In contrast to the previous case, this is more tractable because although we can have a lot of flights, as we've seen, we have relatively small number of clusters. So that's an easier thing to deal with for our limited civil engineering minds. So here's some words about how we do it. And although we've said we've assigned the flights to clusters, that's what we're trying to model, we really think of this in terms of the nominal routes. So we saw before, let me back up, just to remind you, each of these clusters has a white route. What is that? That is one of the itineraries in that particular cluster. It is the one that is the kind of best representative of the cluster. And what do we mean by that? We solve something called the row median problem to identify that particular trajectory. So it's kind of, if we were thinking of trajectories in 2D space, this would be the point in a given cluster that is closest to the center of the points in that cluster. So when we talk about nominal routes, that's what we're talking about. And we're going to model this assignment of flights to clusters as a model of assigning the flights to these nominal routes. So we decide which cluster or which of these routes flight chose by observing the cluster to which it belongs. So then all of our feature engineering is vastly simplified because we can focus on the nominal routes, which are much fewer in number than all those thousands of itineraries. So basically, using these nominal routes allows time-dependent variables such as traffic management initiatives and convective weather to be characterized in a more efficient way. And just to look ahead, what we're going to be doing is for each particular flight based on its departure time, we will be imagining that it's essentially choosing between those different nominal routes, and we will be estimating what its hypothetical exposure would be for each nominal route to different features that we think are important in determining which route it chooses. And you see some of the factors here. We'll talk more about this later. So we'll talk now a little bit about the feature engineering associated with this. And there's a lot of challenge in actually mapping these different nominal routes to these different features. But here are some of the different things that we look at. The top one here is the wind field. So that's based on wind data. We'll talk more about that later. This one is capturing the presence of convective weather. This one is capturing the presence of a certain traffic management initiative called an MIT restriction, which reduces the permitted flows on certain routes at certain times. This is capturing other weather information based on surface conditions such as squalls and rain. This captures special use airspace that is active. And finally, this one captures airspace flow program restrictions, which is another way like MIT's of metering flow in the airspace, particularly in cases where there's convective weather that reduces the capacity of certain airspace. So what we basically do here is we start with our nominal routes. Those are the white ones, and remember that these are actual flown itineraries that happen to be the kind of best representative of each cluster. Now, it was flown at a particular time, but what we're going to do is for any particular flight, based on its departure time, we're going to construct a new nominal route, which is spatially identical to the previous one, but we imagine it's departing at the departure time of flight I. This enables us to extract the features that are relevant for all those different features that we looked at before, and get the appropriate time for which to extract those features. There's some data discretization here to enable us to do this. So we take, say, the original polygons that describe convective weather and turn that into a binary data set. You can see the squares there that we use. That's basically on or off, depicting the presence of convective weather. And then we basically, using that kind of matching and discretization, we match each nominal route with features that would be the appropriate features given the departure time of our flight whose choice we're trying to model. So that's the basic strategy there. And so there's a matching involved. So this is the matching for convective weather. I won't get into details here, but we're basically coming up with a metric to capture the exposure of a particular nominal route at a particular time to convective weather based on the proximity of that weather to the route. This is matching for the wind. So in this case, we're trying to characterize kind of the total additional wind distance that this flight would be able to cover if it were based on the particular wind field that it encompasses. So if this value is positive in the way that we represent it, that means that there is a tailwind, and that's a good thing. So if it's negative, that means that the wind is working against us. And then we have these MIT restrictions. There's not time here for a tutorial on all these different kind of TMI initiatives, but basically there's a kind of initiative that sets a minimum space, minimum distance and trail for flights on particular routes, and it means that the flights will have to be vectored or held or slowed down if they are subject to the MIT. So for each route, again, based on the particular time of a given flight, we figure out what MITs it would have encountered. And finally, this is the summary of all the features that we determined for each of these routes, each of these nominal routes. Now we are going to use this in a very conventional modeling framework, a route choice model based on either logit or nested logit. So we basically assign each of those routes a particular utility, which we estimate the coefficients of the utility in this here. And so basically there's a coefficient associated with each of those features. And then the flights will be more attracted to those routes with a higher V-score. And by observing the actual choices that the flights take, we are able to extract estimates for the values of the betas. So this is what we get when we do that. And so basically negative numbers mean that these features make the route less attractive, and the positive numbers means that it makes the route more attractive. The number of asterisks indicates the statistical significance. And the main messages here is we see the degree to which flights avoid convective weather, that they chase the wind. You see the blue box, positive values indicate that a greater tailwind makes the route more attractive. And they do try to avoid TMIs, in particular MIT restrictions and airspace flow program restrictions. And in some cases, although not all, there's evidence that they avoid active special use airspace as well. This is another version of this. Some of you who are more into this kind of modeling know that there's a more sophisticated version called a nested model that recognizes that different routes are kind of more similar to each other than they are to other routes. And in this context, we say that they form a nest, and we're able also to model these kinds of nesting effects. Qualitatively, the basic results are the same, except we do find some nesting effects where certain routes are sort of closer substitutes for other routes. Finally, this is actually based on another analysis that we did, but it kind of summarizes how important are these different features that we look at in terms of determining which route a particular flight takes. And we see quite a bit of consistency here in terms of the relative importance of different routes. So across all 5 OD pairs, wind is the single most important factor. Thunderstorms is the second or third most important. Another variable based on surface weather, rain is also relatively important. MITs in most cases are a fairly important factor. And then we see a number of other factors that are relatively unimportant. But the main message here is that we are able to extract the factors that drive these route choices, and we're also see a good deal of consistency across different OD pairs in terms of their relative importance. All right. Next, really briefly, I want to talk about another kind of trajectory prediction. And the main difference here is that instead of imagining that we have a flight and it's got a set of predetermined alternative routes, and we're modeling which route the flight takes. In this case, we're actually going to model the trajectory and predict its trajectory in a more, less structured way, a less question of the choice of discrete alternatives, and more predicting what the actual trajectory will be. So we imagine a flight and it's at some particular point, it sees a cube of different conditions involving wind, convective weather, temperature, and other factors. And what we imagine is that its next location will be determined by that set of features. And what we're going to try to do in our modeling is learn the relationships that enable us to use these features to predict where the flight will be next. So we have this 2D grid. You see a particular yellow aircraft there that's a blow up. And basically, it's looking in our model at this set of features ahead of it. And some of the features include wind, weather, and time. So we end up, and this is how we actually characterize this in more detail. So this is the temperature cube. This is the convective weather cube. This is a binary 1-0 representation of convective weather, westerly wind speed, and southerly wind speed. And then through the magic of convolutional neural networks, we take those features and take a set of historical flight trajectories and try to model the next position of an aircraft based on how historically aircraft have flown in comparable conditions. So this is some of the looking under the hood of the CNN model. And this is one particular feature map that comes out. So this is the information that is contained in the different cubes. For example, the top one is convective weather. I think the second one is temperature, and these other two are winds in the two directions. And the key kind of message here, if you're an aficionado of these kinds of models, is that the convolutional layers capture some of these features. So for example, we see that there's a close correspondence between the general appearance of the convolutional layers 1 and 2 here and the convective weather feature. Likewise for 7 and 8, and we see similar things here and here for the wind features. So this is just an indication that the model is picking up features that actually are important in affecting the trajectory. Out of this comes predictions that look like this. Notice it doesn't involve any kind of discrete choice, but what we have here is first, this is the flown trajectory at the time of the prediction, and then the predicted trajectory based on the model we just looked at is the purple line. We can also see what the flight actually did. That's the dashed blue line. We see what the flight plan said. That's the red line. One thing we also see is that we are able in this process to not just get a point predictions, but a confidence interval around the trajectory. That's what the green, it looks like a cloud, kind of represents. And some general lessons that we get from this are that in most cases, the predicted track follows the actual track. In the vast majority of cases, the predicted track is much closer than the flight plan as a predictor of what will happen. And also generally the deviation of the actual track from the predicted track is kind of consistent with the uncertainty that's expressed in the green cloud here. All right. I've got a few minutes left, so I'm going to change topics a little bit, still about trajectories, but now about trajectory anomalies. And so here we're using trajectory modeling for a quite different purpose, and that is to predict unusual trajectories. And some of the work that's been done, and we've participated in some of this work, it does a lot of work to basically find trajectories that are outliers, roughly analogous to the outlier trajectories that we saw in our examples, but more extreme. So very, very unusual trajectories on a given day. And then we view those unusual trajectories as a sign of some issue. It may well be a safety issue. So we kind of look at those trajectories and see what they tell us about unusual situations in a given airport. NASA does have a tool that a team led by ATEC, but we participated in, developed, so they can do this on a next day basis for JFK Airport. When we look at that work, one thing that I noticed is that typically these unusual trajectories, there's some quite identifiable reason that they're unusual. And one such feature is that they were a flight that had a go-around. So go-arounds are widely recognized atypical flight approach procedure. And so we're going to be focusing here not on just general trajectory anomalies, but specifically on go-arounds. So I think most of us know what a go-around is. A good number of us have probably participated as a passenger in a go-round. We use some methods to predict these go-rounds, both a real-time prediction with a hidden Markov model, a statistical model, and on top of these are two earlier steps we have to take. One is actually detecting the go-arounds using trajectories, and another is looking at the features that we think might affect the incidence of a go-around. So we spent some time just detecting go-arounds, and this is what the detection kind of looks like. So we have flights here where we have altitude and time. So these two plots indicate respectively the distance from the airport and the altitude of the airport as it approaches the runway. This is a standard approach to a runway, and this is what we see with a go-around. So we get a certain point, and then the flight starts to climb and move further away from the runway. So we're able to detect the go-arounds this way. We get about 0.4% of the flights at JFK are go-rounds, and that's a fairly common rule of thumb across major airports in the US. So we're going to try to predict these go-arounds, and we did this in a couple of different ways. One is a set of static models. So at different distances from the airport, we get a set of features that we then use to see if those features are predictive of a go-around. So we have a training set and a test set at 10 nautical miles, 9 nautical miles, 2 nautical miles. And we have a set of features that we look at. These include features related to the geometry and the speed of the approach, the separation of the aircraft in question from the lead aircraft. We see some patterns where if there's one go-around in a given time, that tends to suggest there'll be other go-arounds, so that's what we call the clustering effect. We're also interested in the effects of surface operations. One reason for go-arounds is to avoid simultaneous runway occupancy, and so in order to be able to look at that, we have to see what the aircraft on the surface are doing. So that data is also ingested in these models. So we have some statistical models that we use to predict that. And here's one result in terms of the factors that have the greatest effect at 5 nautical miles on the incidence of a go-around. So you see it's a combination of visibility factors and factors related to the flight trajectory, as well as some other factors that are less important. Another kind of model that we've done, and this will be my last discussion, is to have real-time predictions. So we're using an output hidden Markov model for this, where we imagine as the flight approaches to the runway, it has a hidden state, and depending on the state that it's in, there's some probability that it will engage in a go-round. And so we imagine the flight going through a succession of these hidden states. We learn from the data information about what the number of these hidden states and what variables correlate with them. In an ideal world, we'd have semantic descriptions of them. We're not quite there yet. But in the end, we're able to do something like this, and we're actually quite excited about the possibility of having this become an actual tool at some time in the future, where for a given flight, it's possible to, in real time, get these dynamic predictions of the probability of a go-round. So here's a particular example of what this looked at for one of our historical flights. So at 10 nautical miles, the go-round was quite unlikely, but then starting at 8 nautical miles, we begin to see this probability creep up, and this was a flight that actually did have a go-round. So we think that the possibility of having this information be made available to pilots and controllers in real time is of some interest, both so that they might take actions to reduce the need for the go-round or be more ready if a go-round is needed. This just shows how the probabilities kind of change gradually with our hidden Markov model that's explicitly dynamic compared to a random forest model that kind of just throws all the data in and doesn't look at this dynamic structure. So conclusions, we've seen that trajectory analysis is kind of a canonical application of data science to aviation. And we've seen that these methods can be used to enable us to understand things like factors that influence flight trajectory assignment, factors that contribute to the risk of anomalous trajectory events, such as go-rounds. In addition to understanding, there's also prediction. So we looked at the trajectory evolution prediction using the generative model, and we looked at the dynamic models to predict the risk of a go-round. Obviously, there are many, many other applications of these tools. And although I focused here on the legacy system, there's lots of potential for these tools to also be used in the unmanned and urban air mobility domains. All right, thank you so much for your attention. Hope it was not too painful. And if there are any questions, I am ready.
Thanks a lot, Professor Hansen. Yeah, we'll open it up to questions right now. If you have a question, just please feel free to unmute your mic and just directly ask.
Hi, I have a question about this trajectory assignment problem.
Yes.
So you based your approach on nominal trajectories, but you know for each flight its departure and arrival time, right?
Yeah, so when we say nominal trajectory, we change the features of that trajectory based on that time.
Yeah, but if instead of, or in addition maybe to nominal trajectories, you used the original trajectories maybe after step 0, after this cleaning step, for which you know the actual arrival and departure time for each of them, and that probably would lead you to easier matching between these trajectories and flights. And then you know which of these original trajectories are in which cluster, so you can go from these trajectories to clusters. And wouldn't it make it easier or did I miss something?
Well, I probably missed something, but I think I just restating what you said in the way that I would think of it. So we have a particular flight, and we look not at the nominal trajectory, but some other trajectory that for that particular, I'm sorry?
Original trajectories for which you know exactly the timing information.
Yeah, we know that time and information, but what we need in these models, we have to look at all the possibilities. So we know for that particular flight what its trajectory was, clearly, but we need to say, well, why was it this trajectory and not any of these other n-1 trajectories? And in principle, we could try to answer that question. I guess I'd say it's a much more difficult analysis than one that focuses on the nominal trajectories. And the key thing is we have to look at not just the road that was taken, but all the roads not taken. And the features of all those untaken routes are dependent upon the time of the particular flight whose choice we're modeling. So there's a lot of extra computation there that we have not taken on yet.
Okay, but what I meant that it's not a replacement of what you did for clustering, for defining the nominal trajectories. But once you already know which trajectories are in which cluster, and in addition to this, you use this timing information for original trajectories, maybe it would be an additional information that you could use to simplify this matching between nominal trajectories and flights.
Maybe we should talk offline about that. I suspect that it's a very good suggestion, but I just need to understand it better than my slow mind can do at the moment. So if you can send me an email afterwards, I'd be happy to further that conversation.
Okay, thank you, I will.
Okay, great. Are there any other questions? Okay. Well, on that note, we do have Saba from NASA Academic Mission Services who just wanted to give a concluding note. And after that, we will close the Zoom meeting. Thanks again, Pawan, Professor. Oh, yep.
Pawan, quick question. So yeah. You said you were recording this thing, right? So
yes. Yep.
Where could I get the recording?
Yeah, so the recording, once Zoom is able to wrap it all up into a neat video file, we will post that in the various channels, whether it's the listserv or the website itself. So stay tuned on where it will be found.
Thanks.
Yeah.
Just one more question.
Sure.
Is it possible to get a copy of the slides that you used for the presentation?
Yes.
Should I just send you my email and you could send it to me, or could it be posted maybe?
Tom, we're collecting all the presentations at a place and then we'll eventually share all of them. So you should have a repository.
Okay, great.
But Tom, don't hesitate to just send me an email if you want to get it more quickly.
Okay, great. Thank you.
Great, thanks everyone. Saba, can you unmute your mic and give a few words as well? Thank you.
Thanks, Pavan. From the NAMS team, I just wanted to say thank you everyone for your patience as we took the seminar series to an online platform, and we will continue to work with UC Berkeley and send out joint notices for upcoming seminars. They will all take place every Wednesday at 11:10 a.m. and we will have the presentations and the video recording posted both on the UC Berkeley platform and on the NAMS platform. So thank you, Pavan.
Thanks so much, Saba. Thank you so much again, Professor Hansen, for giving this talk. I think it actually is quite refreshing and informative to have these Zoom meetings. So this was fantastic. And for everyone else, stay tuned for next week. We will be updating you on next week's speaker.
Before we end, I had a quick question. Is it possible, especially for the students, to start this meeting at 11 or 11:05, just in case, checking? Because there are no more classes anymore, right?
Yeah, I mean, I think that was something that we had been discussing. There was a note that starting slightly later than on the hour can lead to better communication bandwidth. So there was that note, but having said that, maybe we can discuss that offline and we'll inform everyone of whether we'll have an 11 a.m. or an 11:10 a.m. start. Okay. Okay, thank you everyone. And we look forward to having our next speaker next week. And thanks again, Professor Hansen. We appreciate it.
Thank you.